Okay, good morning. Sorry for the small delay in getting the live stream up and going. So it's always a pleasure to be back here on the first Sunday of every month, 15 years now, with a new topic related to science, technology, and its connections to the world. And there is no better topic that we could have chosen than to celebrate the 75th anniversary, the 75th birthday of the very humble and tiny transistor, the device that makes everything that we do in our world today, including for those who are watching online, this streaming of this thing possible. It makes all our electronics possible. And to tell us about that is Satya. Of course, before I introduce him, just in case anybody is here for the first time or is listening to us online for the first time, Chai and Y is a outreach offering of TIFR, which happens on the first Sunday of every month physically at Prithvi Theatre in Juhu, and also online on Zoom and YouTube. And the third Sunday of the month, we are at Ruparel College in Matunga, Mumbai. And if a month has a fifth Sunday, we are live streaming from Colaba, from a lab. Now, just the next Sunday, the next first Sunday of the month, the next session over here will be the first Sunday of March, which is also the Sunday nearest to Holi. So that will be a session which will have a link to color. So I don't exactly know the topic as yet, but it will be linked to color, as the Holi session is always something related to color. 2 weeks from now, we will be at Ruparel College, and that session is about today is February 5th, so 14 days from now is February 19th, which happens to be Copernicus's birthday, and hence we are going to have a thing on astronomy, which I think tentatively the speaker has given us a title which sounds very nice. It's called Yetara Votara Hartara. So that's going to be coming up at Ruparel College 2 weeks from now. But today we're going to be looking at the transistor, and to tell us more is Satya. Now, Satya is a veteran of Chai and Y. This is his probably third one, I think, and he's been here at this venue before as well. Satya is how do I call him? A neutrino hunter. So he spent most of his life tracking, hunting these very elusive particles called neutrinos. And to do that, he has we'll come to that. We'll come to that. Just a second. Let me just introduce him. We'll let him start off, and then we'll. So to do, obviously, if you are doing any kind of detection of high energy particles, high energy particle physics, it requires a lot of electronics, and hence Satya has also been one of the people at TIFR who has been at the forefront of some of the most advanced analog and digital electronics that are needed for these particle physics experiments, very large particle physics experiments, and specializes in something called a RPC, a resistive plate chamber, on which he has talked about before. But he has also spent a lot of time volunteering his time talking to college students and all about electronics as part of the IEEE. Sorry. And in his role with the IEEE, he has been popularizing everything in electronics, including the transistor. And today we'll hear from him about the 75 years of the transistor. So over to you. And if you have questions on neutrinos, I am sure Satya will be delighted to take them. Catch him. He's always ready to talk about particle physics. So talk to him. But let's share your screen and get started with it right now. Where do we
last time? But yeah, okay. This one. Share. That's it.
That's it, and we'll hide floating controls. Okay.
Yeah. Okay. All done.
The mic is only for the online audience. I hope people can listen.
Oh yeah, I hope so.
Yeah.
Yeah, I can speak louder if you want. Please feel free to interrupt me on that. And once again, it's always a great pleasure to speak at Chai and Y, and of course, this is a magnificent venue everybody look forward to, and I also look forward to a lot of interaction that happens both during the designated 1 hour and also maybe afterwards when the probably live transmission is going to close. Thanks once again, Arnab, for your very kind introduction. Yeah, as you said, today we are going to kind of celebrate transistors. We are going to celebrate transistor in its birth. And the title it says is tiny. Tiny, of course, is for the size, which you will really see a little later, what size we are talking about. But at the same time, it is mighty because the whole world, as Arnab mentioned, and also you will hear more in the talk, that everything that we essentially can do, I mean, the whole civilization in some way, if I can use that word, has been so influenced by this single device. And possibly, if you want to list a number of such things which change the world the way we live in today, probably transistor comes on the top row of this place. So that is why this contrasting title of tiny and mighty. And so what I have today for you is, I will of course try to, since it's a bit of a commemorative kind of a talk, there will be a lot of historical kind of slides that will take you through how the whole thing happened. And I tend to be a little less technical on that front to give maybe more of anecdotes and the way things have gone in the timeline. But as we go along, transistor size will come down, the transistor numbers will go up, and so is the little bit of complexity of the talk. I'll try to kind of say where is transistor heading, and for example, how is it going to look like? I'm not sure if I will be alive when it turns 100, and if I'm alive, probably I'll come on a wheelchair and give a talk in the same auditorium. I'm sure Chai and Wai will be there 25 years from now as well. And then we'll speak and say, oh, transistor looks like this today, and so on and so forth. So that is my scheme of things. So the first half will be more of history, and second half, just like any popular Hindi movie, will be more interesting because it will pick up speed, right? Okay, so it's a long intro. So don't see this moving. Okay, I have to, I think, click on. Yeah, so okay, I can move. Okay, so the point is that when you talk about any such a long journey, it's not really easy to pinpoint and exactly say where is the T0, where is the timeline. Though we are commemorating for a particular date and time, which will come later. But look at this, and one is actually talking about, when you say something of transistor, we are talking something prehistory, if you can call that, and you say that the first patent of any semiconductor device that controls the so-called flow of current, flow of charges, was actually filed way back in 1928, right? Much before where we are celebrating 75 years. And if that is not enough, I will actually come back a couple of slides later, trying to even go beyond, before this date, all the way to 1901. That is the interesting story, but that will take up later. But today, at this moment, let us talk about this gentleman, Linenfeld, who is basically a German. And if you look at the kind of general device, as I promised, I'm not going to kind of go and start talking bolts and nuts of the thing here. But if you just see, even from the place where you are sitting, this device looks more like a MOS device, metal oxide semiconductor device, which we will briefly talk about later, rather than the first transistor that we are going to describe soon. Okay, so it's very interesting. That's why this word future kind of comes in. And of course, MOS devices have become very, very popular and dominated, in fact, the whole world until after 1980s. So the point I was trying to kind of say that is, there are these aluminum layers, there is aluminum oxide, and you have the so-called source, the gate and drain, etc. Exactly like what we saw devices much later, 30, 40, 50 years later. So that is how the whole story begins. And this person, of course, besides what we call theoretical creator of the transistor, just because the entire the recipe of what a transistor is and how it should work, how it should feel, how it should work, etc., is all done by him, except that he's a person who has worked more of theoretizing some of the concepts of this, rather than actually building something that could be claimed to be a working device and so on. But I also want to take this opportunity to introduce this man, who is German. He is actually also the first person to describe as far away, like radiation of X-ray tubes, etc., how they are visible to the human eye. And it took 20, 30 years later, someone to kind of take the field from where he left and move forward. So people are, generally, they do things which are not necessarily just only zeroing onto a small field, but it will have repercussions on lot of things to happen. Of course, before the transistor, it's not that there is no device which works on flow of charges or current. We all know the so-called vacuum tubes, which were ruling 20, 30 years before all these kind of things happened in 1947. So the so-called cathode here, and then there is a filament which will get heated up, and you have the, instead of gate, it's like a grid, and then instead of collector here, you have a plate where the charges are collected. But the problem with that is there were many such applications which people found it's very hard. They're very bulky. They require huge power to transmit, to use. So people started thinking that, look, this is okay. This is obviously something really, something new that has come on the horizon, where you can actually control the flow of charges by the grid and so on. And that had fantastic applications. But what is more important is people wanted to see something of an equivalent of solid state device, vacuum, and all these bulky things like that comes in. For example, this ENIAC computer weighed almost 30, 40 tons and gulping something like 100, 200 kilowatts of power. So therefore, the Bell Labs in 1945 said that, okay, look, let us, we know that this device works. So it actually summoned these three guys and said that, why can't you work on a device which is tiny, smaller, less consuming power, and also maybe, things can see a future. So then the team started working. But remember, this is what I wanted to kind of say. So they actually use linear field concept in some way. Okay. But the problem is, see, this guy was ahead of his time. Actually, they couldn't get that device to work because it is not the device that I'm going to show you later on where they stumbled upon. But this device is something way ahead of it. And in principle, the device is much different than what people could think of on those lines. Okay. In fact, one of these, Warden, in fact, said that it was because of a particular phenomena called surface electronic states, which one expects, the electron states close to the edge of the material, any solid material, and so on. Anyway, whatever the reason may be, but things just did not work there. So that is how you see this so-called point contact transistor came into being. This is own creation of this team, as I said, led by Shockley. But I'll tell you a little bit more details about it. But basically, they want to look for other options because they failed with the linear field thing. The so-called concept is something inject, something collect. The transistor essentially is that somebody is injecting, somebody is actually collecting. So that's how you call them as, emitter, and you call collector of a transistor. But the way they did is they actually wanted to get that into a semiconductor base by using.
If you point on the screen.
Oh, okay. That doesn't go. Okay. Okay.
Look that way, they only see your back.
Okay.
So maybe you can just.
Okay.
You don't point.
Okay.
All right.
Yeah. Fine. Okay. Yeah. Okay. Thanks for that. Yeah. So therefore, what they actually did is, they wanted to kind of make a base with two contacts, which you could already see them. Okay. So this is the base, and there is a contact that you can see like a wedge, which is actually. Okay. This is okay. Okay. So finally, what they did is somewhere around December middle in 1947, somehow they were able to kind of engineer and solve this problem where how you can actually point to a base with a very finite kind of a gap between them. I'll show you a picture. So even though, out of these three, Shockley somehow was not so much part of these experiments that were going on in 1947. But then, we all know that he was the leader of this team. And this picture that you see on the right, where there's two parts where they were actually working with the device, and on the left, the actual device, the very first device that they built. This picture is very kind of iconic, right? Okay, now let us look at a little bit more what the device looks like. So if you kind of look at on the right, what you have is this slab of very thin slab of germanium. Okay, and then like a plastic, it's a wedge, it's a triangular piece which is essentially kind of covered on the bottom as with a gold foil. It's a conducting foil, and then on one end you have emitter, on the other hand you have collector. But at the tip of it, it's not like it is continuously connected, but you keep a very, very finite, very, very small gap, so that that is what like kind of works for actually as a transistor, as a kind of device contact. Okay, now doing that is non-trivial, because many times it is like trial and error. In some way, to make the contact very unique, they kind of have a funny looking shaped spring. You can see on the in the actual picture that it is shown in the middle. So very funny way, like an orthogonal fashion, the spring is kind of bent so that they can apply precisely the pressure that they kind of want. So what is critical here is a very thin razor cut between the base and emitter and collector. So the tip of this point, base is of course is the kind of slab. Now, if you look at also on the left, there is a yeah. Yeah, they're touching the germanium, but but there is so it is not exactly the vertex of the triangle. There is a gap. So it is not that the gold foil is like this. The gold foil, if I can make it, it is something like this. Okay. Yeah, it's a down. Yes, that's right. Yeah. Okay. So of course, on the left, you can actually see that there is a model of what the first one that is built. In fact, a model of such was also there in IEEE headquarters, incidentally. But okay. So this is the very, very first device, and then as I said, it required a lot of mechanical precision, cutting it exactly at the apex, so that you create very, very closely spaced, but electrically, not conducting. So that is something independent. That is what is kind of required. And this device, obviously, it took a lot of time for them to kind of finalize it, because this all not like a technology that you would have seen later, right? Okay. So what I wanted to bring this is not that I or you want to read this, but the kind of doing science or engineering those days, it's very important that everything that you see in the lab, everything that you observe, you actually record in a notebook, because you never know later on, what are kind of things are going to kind of happen. And if somebody is kind of doing something so fundamental, something that is going to kind of change world, and it is good that it is documented well. And I was trying to kind of read this handwriting, but it is very interesting that they actually wrote everything about how they found. They did not have readings or table or whatever, but they wrote every value. They said, what kind of signal they fed and what kind of gain they observed, and so on and so forth. And important thing is that even the notebook had a proper date, time, everything looked like as if they could see that this is going to kind of a discovery that is going to be remembered forever. And at the end, if you look at, they even written who are the people present in the lab, something like a witness to this particular observation. So because sometimes things do happen, since he asked about neutrino, I can't, kind of resist by saying, we did an experiment in Kolar gold fields. We observed certain phenomena and then published on 1965, August 15th. But then there's another group competing with us. They actually observed it a few days later, but they happened to publish it in the journal before us, and so on. So it's very important that you actually timestamp all these kind of a thing. So it's important that, very nicely these people have documented that it kind of happened that way. Now, so even though for this particular thing that happened, actually incidentally it was on 24th December 1947, but they filed the patent in June sometime next year. And for this particular transistor design, of course, it took some time before the patent was issued. Actually, you can see on the right, the second picture from the top, you could actually see that these devices now look more sophisticated, at least looking much different than the crude piece that what it was done. Now, so all these egos, clashes, are common in the scientific world. So even though the Shockley was the leader, somehow it so happened that he was left out when the actual discovery had happened. In fact, when the readings were taken, he was not around. So he was very unhappy, and then sometimes being unhappy and being jealous, being egoistic probably helps a lot. In this case, normally when you think that your colleagues have bypassed you and went ahead, he actually got very upset about it. He said, look, I mean, sitting in a hotel, he said, I'm going to kind of make a device which is much, much better than what these guys did, even though he was part of that particular thing. And that is great thing because it actually brought in very quickly, very, very quickly, what we call today junction transistors. It's a huge leap from a point contact to actual junction transistor. Today, BJT, so-called, is actually junction transistor, which has ruled world for many, many years. So he very quickly kind of developed. And then, of course, as I said before, the point contact transistor is a bit difficult to even set up and much more difficult to kind of operate it. And, the efficacy, etc., are not so good because the contacts are something that can make or break because it is all mechanically aligned, right? You saw that to a kind of a spring. Now, I want to digress a little bit, not so much, but, bringing this again, J.C. Bose, who every time now and then in the history, you will keep finding that he had done really fundamental work, but then, the limelight is actually gone to someone else. You remember the story of Marconi and J.C. Bose, right? Now, this is another example. Way back in 1901, way ahead of even, Linus Feld, where you're talking about 1928, we are talking about 1901. He actually kind of set up using a galena, which is lead sulfide crystal. And then again, the same thing, contacting with a metal point. And he used that as a detector. It's not as a kind of transistor or whatever, but as a detector to detect microwaves, for example, okay? Electromagnetic, millimeter electromagnetic wave. That is what his field of research at that time. So he actually filed a patent way back in 1901. This is basically point contact semiconductor, or you can say rectifier diode for detecting radio signals. It's a diode. It's not actually a transistor as it is, but it is first ever semiconductor device that is patented because it's way before 1928. So this is some always we don't know enough of J.C. Bose. As you keep digging, you will find that he had done wide range of things all the way starting end to end. But this discovery too is something which is not so well known as rest of the other things. Okay, so I told you that I actually on the right I mentioned to you about the patented device. At the bottom on the left you can actually see J.C. Bose and with his crystal detector, the actual model of the actual piece. So since Shockley started working, so his patent of junction transistor followed soon after that. Okay, that was in 1948, but it took almost a couple of years, 2-3 years to kind of patent. Now you can actually see on the right, that picture of transistor is more similar to what you and me now know, right? Basically NP, and there are these blocks of semiconductors. So one good thing about the way it happened for the other discovery or patent is AT&T couldn't really make it like a completely a secret kind of a discovery, because that is something which is a government approved institute. So they were kind of bound to share the knowledge to everyone. So this is one good thing happened not only for the transistors, but later when people actually developed integrated circuits, the same thing kind of happened, that you need to quickly, the development happened much faster because it was not governed by all the, very strict regime of patents and royalties and so on and so forth, right? So therefore it become much easier to kind of share this semiconductor technology. And as I said later on, when the integrated device kind of came out. Now, see, this is in history of science in general and history of maybe technology and everywhere else. People tend to get, I don't know how this happens, but people tend to get similar ideas at similar time parallelly. And remember, we are not talking about the days of internet and so on. Somebody is sitting in South Africa doing an experiment and said that this is atmospheric neutrinos. Sorry, I keep coming to neutrinos again and again. But then somebody in India sitting 2.5 kilometers, 2.7 kilometers below, looking the same idea. See, these are, and at the same time, it's not just somebody 100 years ahead, but at the same time doing things, and it is in a way very interesting. But the repercussions are, of course, needed, because you can't have such a major discoveries to happen with one measurement or one observation. When all this were happening in United States, somewhere in Germany, in Europe, people again sitting and developing device which is almost the same, except they call for some reason transitron, and that is again 1948. Okay, and all these are happening kind of together. And but then again, you can see these times play a big role. By the time these people came out, okay, Bell Labs have already announced in publicly in around June 1948, and there is some entry in the notebook, because of course patent came much later, but there is an evidence. That is what I wanted to mention, that how important it is you document everything that you have been doing. Now here is a notebook which has a date and time stamp, and which told you that this work was done ahead, not so much ahead of, maybe few months, few years before that it happened in, let us say, in Germany. But if you look at the device, it's something very, very, very similar. So, well, you can call that as, if you still want to give a good credit, you say the first transistor in Europe. I mean, okay. So that is also a kind of a good story. And the people here are, of course, basically French guys, Halbert and Welkerhard. Okay. So now the name comes, right? The device is already there, and you know how it works, and etc. etc. But people wanted, yeah, it's also point contact. No, it's also point contact. Yeah, thanks for reminding that. It's also point contact, similar, exactly. In fact, maybe I should kind of show on the right. So you can see the structure. It is exactly similar to what these guys in the United States did. Okay, because when you want to get a good a name for it, okay, the semiconductor, because triode exists, so people said a semiconductor triode. But Breton said that no, it should be not two words, it should be one word, and so on. And this word trans resistance, you know, in a transistor you have base to emitter junction, you have base to collector junction. These two resistances are for different. From base to emitter, it's a low resistance. From base to collector is higher resistance. You are actually controlling current flow through this, and changing the change of resistance in some way. Trans change of resistance. So trans resistance, trans resistor, transistor. So that is how things came. By the time things like thermistor or maybe varistor, variable resistor, etc., they're already popular names. So therefore, to keep that in sync, so it was decided that we will call that as, there's a American radio frequency RF engineer, radio engineer by name Pierce, who actually coined this word called transistor. I spent a little more time than I should have spent about the name, because I'll actually come back and say there are also brand new concepts of something making equivalent of a transistor, something else. Maybe if I have time, I'll going to kind of show. You want to say something?
Yeah. I just want to say that Welker is actually more important than you may think.
Okay.
Because he figured out that he has no chance with silicon transistors and germanium transistors. AT&T is way ahead. So he gave up on silicon. And he's the first guy to work on gallium arsenide.
Okay. Oh, okay. I didn't know that.
I mean, all that I do is thanks to
Welker. Actually Welker. I see. Oh, I didn't know this. This is interesting.
So it's the stuff that we do.
Okay. Okay. Thanks for the. Yeah. Okay. I hope there will be something coming in. Otherwise, you can catch hold of Arnab or maybe during the question answers. Yeah. So again, flipping back to Shockley, because these developments are happening in parallel. So he, as I said, he had kind of worked on the complete device physics in 1948, and then, as I said, he filed his patent. But what is also important is this very nice book way back in 1950, where he kind of talks about the two carriers, electrons and holes inside the semiconductor. That is actually the Bible even today. But that is what I think has become, when you work on, there are two aspects of a brand new device. Arnab talked about me working on a device called resistive plate chambers. Now, I mean, there are two aspects to this. One is you make a device work or detector work and use it for the purpose, for example, in this case, to detect particles. The other thing is when you make a device like a transistor, you want to make a useful device by which you amplify, let us say, a tiny signal that you give it at the base or somewhere, right? But but how does it work? And what is the device physics that you have is equally important, because that is what makes the entire operation understandable. And at the same time, if one needs to kind of find new insights or even a new device or a new material or whatever, like for example, you asked, how the material changed from gallium, silicon to germanium or gallium arsenide, etc. So that requires so much about what the device physics is. So he really contributed enormously to kind of put transistor, if I can say, on a strong footing, not just saying that I have given a signal, it amplified, but why did it amplify is actually all came from this kind of a book. Now, also the fact that from this almost like, mechanical transistor, if I can use that word, to kind of junction transistor, which has two main kind of ways to produce. One is actually growing. The other one is, kind of an alloy making, but that will come to that. So that he is able to kind of establish. Of course, to some extent, how well you can, get a very good transistor to work, it actually becomes, depends on the quality of germanium, the material that you use, because you're all playing with carrier densities, right? Doping, what you call. So therefore, it was very important that you create very good, germanium crystals. Now, this is again the last slide. When if I have, if you all still have not slept off by the time, I'll probably show something which really comes to this, that for such a development, you require heterogeneous skilled people. Now, when you say germanium, it requires a very pure form of crystal. Now, there has to be a group of people who understand pure material science and say that, okay, here is how I can clean so-called unclean germanium into clean levels of doping or concentration that it will give you a good result. And that came at this time from two of his colleagues, okay, Gordon Thiel and Morgan Sparks, who are also from Bell Labs, who actually were mainly responsible to kind of, they are called crystal growers. And I'm sure many of you know how important it is in the condensed matter material science that there is an expert who can grow crystals as per the specifications, for example. Okay, so I thought I had one more slide, but okay, maybe I'll get on to later. So here, the main contrasting difference is that you have one point contact transistor, which, as some of you asked this question, we are only talking about a surface kind of a kind of physics that you can think of. So you have an emitter, a slab of, let us say, N-type material, germanium material, which is on the top, and there is a bulk which is N-type. And if you can divide they are actually divided top, which is like a yellow or orange part and the blue part. And then, but the devices wise, you have an emitter corner, you have a collector corner, and the current that is flowing from emitter side or collector side. It's exactly like what a modern transistor is, but you can see the entire thing that is happening at actual transistor operation is limited on the surface in some way. On the other hand, the BJT or the bipolar junction transistor, the way it happens is a bulk kind of a process. You have an N-type material all through. There's a what you call band gap, for example. In this case, it's a P-type material, and there's an N-type material. It's a bulk top to bottom, right? But at the same time, both offer a region which is depletion region, but and you also what you call bias. You also apply biases to emitter to base and collector to base. The process is exactly similar, okay, except that bipolar junction transistor is something which works on carrier densities the way that we know of today, whereas point, it's contact, right? It's just a contact that you have on the surface. Is how originally the device was kind of made in the beginning. Okay, so the thing happened in 1947, we said, okay, just like it always happens for Nobel Prize. So they got this prize in 1956 for this award. And please note, Shockley is very much there. He grabbed 1/3 of the money, even though he was unhappy. But at the end of the day, I think he's the person who also directed. He's the team leader of the entire thing. And many of you probably know Barden is also won another Nobel Prize in 1972 for equally interesting, probably more interesting as a science, as a per se science, so-called the theory of superconductivity at a kind of the process, the physics of superconductivity at a micro level. So he shared. He's the only guy who won Nobel Prize in physics twice. Okay, so that is the story about the Nobel Prize. Yeah. So now slowly moving forward. Now when you say that okay, somebody actually made a very crude device called transistor. Now if I want to really productionize, if I want to kind of commercialize in some way, now the processes, the materials, everything has to be perfected. That for example, the let us say the purity of materials and so on. So there were two schools of production thoughts that came out. As I said, one is of actually growing, just like a crystal. You can see on the left, you have a kind of a container, a crucible or a quartz container in which you have the semiconductor material, but you also have to make three terminal device. So you need to kind of have, let us say, if it is an NPN transistor, you could have a P material, but the N has to be doped somewhere in the middle, making like a vertical, as I said, the bulk kind of a cross section. How do you have? So the way you have is this crystal to which you add as a seed material, and then the whole process is, of course, is a recipe how you actually gradually dip this, the frequency, the temperature, and so on, and ensure that there is a clear demarcation of NPN made in case of NPN transistor. The other one is a little bit like making an alloy. So you kind of have a material which is, let us say, an N-type. So you can use that as a base, and you need one contact for emitter and one contact for, let us say, collector. You can use any joint. For example, indium is the most popular joint. You actually do that as an alloy. If you can see on the right side, it's not a chemical process, but it is like an alloy of let us say two metals in this case. One that is used as N-type material, base material, where it is and emitter and collector are kind of tagged onto this externally. So both these methods have become very popular as a precursor to kind of producing this. But soon one hits this, as you are also asking about. The problem is that very early on they kind of realized that germanium, silicon could be a better material because it has a higher band gap. So you can actually build better devices. But the main problem with silicon is silicon compared to germanium is extremely reactive. Okay. So then once again, you require somebody. See, this is the kind of journey of a device. Look at, I mean, the basic concepts or probably it took some time and somebody got on. But to make a real device, they said, look, I mean, you need to find a kind of refining technique. I have a process where I have germanium, but which is not, let us say, very clean. So therefore, how do I make? So this technique is called the zone refining technique. If you see the picture on the left, there are kind of ring-like structures which are actually heaters essentially. Now you have a cylinder of, let us say in this case it is germanium. You kind of slide through the series of this ring, and only the zone that you have at the heating element is going to clean up, and you keep pushing it preferentially, and then you can see that the surface of the germanium, the bulk of the germanium gets purified. This is called zone refining. Means it is not a bulk. You put the entire thing into one, let us say, furnace or something, but this is a piece by piece. Okay, so this was actually done to kind of help people to build their devices. But later on, it was actually become much easier. With silicon, let us say, dioxide SiO2 has become much better properties. The so-called surface passivation, where I want to maintain the cleanliness of the surface. So the way you kind of do it is you clean off the top material, and it kind of automatically forms oxide that prevents further deterioration of the material. So it becomes much easier for you to kind of make devices out of it. All right. So then silicon quickly replaced germanium, because the problem that you had with silicon being very reactive, that kind of got solved, right? So that is the next big step. And one very big step that came out is making what you call planar process. Remember, when you want to manufacture devices, all these, crystal growing or alloy making or any other device, these processes are not amenable to kind of do a foundry-like process. The foundry-like process is much better if I can do a planar kind of surface. It doesn't matter. I can do one layer, and on top of that, I can build another one. I can make structures and so on. Maybe you will see a picture about it. But that again, the guy by name Jack Arnoy from Fairchild, credit goes to him to kind of use the planar kind of process. This is a process design. It is not so much about a device per se, but way back in late 50s, and he actually started using oxides, basically silicon dioxide. So once this process got streamlined, you have this Robert Noyce who actually moved from by the time Shockley actually developed, he started his own company called Shockley Transistor. Then he went to Fairchild, and that has later on become Intel. Okay, it's the same.
The Fairchild story, the Shockley and the traitorous eight and all.
Not really, but maybe after tea break, yeah, we can have that. So these people actually co-invented also later in 60s. What we see as integrated circuits. So you see from already when the transistor is still getting perfected both in terms of material and process, you already could look at that now. I mean, transistor is a single device. And now I'll be able to kind of integrate many of them and start looking at a device as an integrated circuit. Now, integrated circuit required planar kind of process rather than, the mechanical or, alloy or whatever it is. So this is how one has kind of moved forward very quickly within about a period of 10 to 12 years, right? That is where it is. Okay, people then said, okay, if you are ready to kind of use a planar surface, I could also use so-called diffusion process, which is even more easier and more accurate in some way to kind of make the process materials. Okay, so basically it is a process by which the atoms that you put where can actually diffuse from high concentration to lower concentration. You can actually control a very, very precise processes if you want to plant, if you want to build certain structures on it. Okay, so planar, yes, but the process that you use would be diffusion rather than any other processes. And that led to building very, very fine structures, which are necessary for integrated circuits later, has actually paved the way. Okay. And so this is here we have almost future-looking device, which is, took the help of early understanding about the surface states that Bardeen and other guys did, but these people used actually the silicon dioxide, both Dowen and Martin, and they could finally come to what today we call MOS device. And out of all that today we see, 1960s onwards, and today all that devices that are made of and what we use are not so much of BJTs, etc., but MOS devices, CMOS devices. Okay, so that is, I would say, a little bit of a journey part that I wanted to kind of take you from point contact to junction to using different materials and arriving at a process. By the way, the process is very important because even today, I mean, when you say that I'm building certain device, what is important is what is the process that you follow. Now let us change a little bit the gear and then look at when you have reached a certain level of integration, a level of not working as a one unit of a transistor, then the question comes that can I really now start building together, make something where the transistors can interact with around them, maybe tens of them, hundreds of them, thousands of millions of them, trillions of them, and then start building something very useful device. The whole field of this has kind of opened up a brand new field called microelectronics. Of course, it's electronics, but it's micro because it is very, very small in size. And then what is the kind of problem that you would have with building such devices is when you use what these people built as a first point contact device, the devices are quite big dimensionally. So therefore, the problem of even if I operate them at a certain frequency, there is no problem of, let us say the stray capacitances, the problems like that coming into the effect because the devices are quite big in dimension compared to what I'm operating them at. But when I make the same device very tiny, okay, the stray capacitances between various terminals can actually play a big role into that. And also as the sizes become smaller and smaller, as I told, I have to now take care of the interconnections and the problems that I face. So all that comes under one particular kind of field is that if you are an engineer who is actually working on such microelectronics, you have to worry about to compensate for all these bad things that happen because the device sizes become very small now. So with that invent now, when you had integrated circuit, then the question came, okay, how do I kind of define what is small, what is big? But that is just matter of numbers. But today you have the starting from few hundred. So you had one transistor in 1948, right? There was no other single one transistor existed in the world. But then as you grow, as you went along, you found hundreds of transistors making one integrated circuits, and soon, very soon, it becomes so-called very large scale integration, very large scale, putting large number of transistors together, billions of transistors to do one kind of a common function. Transistor using as a switch, transistor using as an amplifier to amplify the signal that you fed is one as a unit. But now if I want to do very complex function, maybe a digital function, the way you see all these devices, you're required to communicate with so many transistors together, right? So that is what has come to be known as very large scale integrated device. So every millimeter of, let us say, a chip would have typically billions of transistors, right? And now the problem that comes very soon, see, you never stop, you are never happy when you reach certain things. So now the question comes is, okay, I want to build an integrated circuit. Okay, maybe you built with 100 transistors, but today you are maybe trillions of transistors. The point is, I would like to typically have very, very fast device. Okay, I would like to have, let us say, the device which consumes very less power. Okay, and thirdly, I want to have a device which occupies very little space. Obviously, right? We all want this. Now, if you look at the contradiction that you have, if you have very fast switching device, obviously it consumes more power, right? And if you want to have a large integrated, let us say trillions of transistors, it also occupies certain space. Now, how do you do this? But the whole game of microelectronics, the whole game of what happened, let us say from 1960s and 70s, is actually to solve this problem of these three competing parameters. And that is exactly the exciting journey that all of us shared as a professionals when we entered, let us say, 70s and 80s into this era. Okay, and of course, the functionality of these devices also have gone leaps and bounds that we will try to kind of see. Okay, so just to give you a kind of feeling like how typically life or life journey of an integrated circuit, right? So you kind of first you start with creating a crystal, okay, which is actually grown in a lab or in a factory or whatever it is. This is what it is, how it is grown. And now you kind of slice these crystal very thin, almost like potato wafer, right? And that is the basic wafer using which you actually start building devices. Could be 4 inch, could be 6 inch, could be 8 inch, as the technology is. And then you use this so-called lithography technique by which you can actually deposit, you can use light essentially to grow structures on top of the wafer. And now that depends on your entire, if I can call that as a master plan of a chip, just like master plan of a building or a quarter. Okay, but then you need to kind of build device by device, transistor by transistor, emitter by emitter, base by base, collector by collector. There is no way to shortcut. So therefore, what is the smallest device that you can make? It depends on the technology that you have. Let us say the lithography technology. What is the best that you can use? What is the smallest wavelength of light that can use to etch the structures on it, make that very, very, very tiny devices and so on, right? Now, so therefore, while the integrated, I mean the density of the chip in some way depends not only on the materials that you use, also the techniques and the tools that are made available by a different field of, let us say, science and technology. In this case, it is, let us say, material science or condensed matter physics, device physics, etc. Okay. Now, when you build so many billions of transistors, you also need to connect them from one to another, because that is what makes your entire circuit the way you look at it. So there will be so many connections horizontally going from device to device. So each one of them, like a pizza, I mean, once each one is kind of integrated well, you kind of slice them, dice them, and then package them. Because ultimately the device is sitting inside, but the inputs, outputs have to come to a place where you are able to kind of solder on the device, right? And that is exactly packaging kind of does. But you may look packaging is something very simple, but it is not so simple, because it also has to take care of a lot of radio frequency interference and other mechanical properties that you need to take out. So before the chip can come to a laptop in your computer, it takes months or even more to actually go through all these processes that are required, right? But if you're a person who want to actually design a chip and then kind of produce them, now that you know how the process works, what I normally say is that no matter what kind of digital logic, for example, that you use, it is only made of these 3 or 4 basic elements. One is, as I told you, you need to connect from point A to point B. There are lots of interconnections that are required, because one transistor to the next one to next one. Imagine that you have trillions of them on a chip. Okay. And the second one is most of the logic functions, you need to kind of implement them. It's what is called combinatorial logic. So I kind of give certain inputs and say combinations of this is going to produce, let us say, the output. I mean, as simple as saying that if it is like Arnab mentioned, is it is the first Sunday of a month, and it is going to be in China and it is going to be in Prithvi and so on. These are logic equations, logic conditions, right? And the third and most interesting thing that really makes the devices work is what is called, a time sequence kind of work. So that means in order that I am able to start lecture, it needs necessarily certain audience to come in. So there is certain sequence or sequential kind of circuit. So there is something basic lines, there is something combinatorial, there is something called a sequential logic. Other than these three, no matter what logic and how you want to use basic elements of transistors, there is no third way of saying that no type of device which I need to implement. All the circuits, how big, whether all that knowledge. So we used to depend on the chips that are produced by factories. Stable. Okay, it gives you, like, if there are 2 output, what are all those conditions, 4 conditions, and what is the output going to be, and so on, right? There is no other way. The fate of the chip is decided by the manufacturer. I come, put it in my circuit, and use that as a truth table, right? There is no other way I can change. Now later on, I mean, when very very sophisticated user point of view things have become common, then it was like said that, okay, can I design my own chip? Okay, this is integrated circuit specifically to my application. I'm not depending on to make my own Boolean logic, right? So now that is a big task, because then I require certain tools which were not available before, and certain skill set which was not existing from a user, which are not expected from a user, right? But then, of course, that is what the progress of this particular industry. The third one, of course, is something in between these two. If you manufacture certain products, it requires, that is a communication product. They all use the same kind of chips, or many computers. It uses, all of them use the same Intel processors, and so on. So there is something in between. There are 3 classes of these kind of chips that have come into kind of being. And this picture, many of you probably familiar. If you have studied engineering in the first year or second year, you go to your lab and your teacher tells that, okay, you connect wires from this to this on a breadboard, and please check the truth table that it serves. Perfectly fine, no problem. All these things work quite well. The problem is, if I actually go ahead and build a big system using such breadboards and small, these kind of integrated circuits, it becomes very unwieldy, and it becomes very tough to kind of do make those kind of circuits work, right? So therefore, what has come up later is that programmable logic. That means it's like a canvas that I buy and bring it to my lab, and I actually write all the logic equations that I want, and someone will help me to convert that logic equations into a code actually download into my chip, and the chip becomes a big. Don't like that logic tomorrow? Okay, no problem. Take that logic back and modify where I have modified, just like any software, recompile it and push it, and that something new. So this programmable logic, and like what I mentioned to before, the field programmable gate arrays, I can actually program this chip in the field. And so that has revolutionized the way the transistors have been placed into a chip, which are now not fixed by wires, but they're actually, the wires themselves are programmable. The function itself is programmable. That has opened up a fantastic new technology in some way. And that is because, nowadays, when you buy a device, they don't ask you to bring the device to a factory to change or upgrade firmware. If you have an internet connection, the person sitting in the factory can actually upload or what you call upgrade the firmware and so on. So that is something new that has kind of come out. So that was possible because instead of making like what you saw, those gates, now you have like blocks of those so-called lookup tables, and then they're all connected to each other. That can be programmed. The connections can be programmed, and what goes in each of these blocks can be programmed. So that is actually made a life of an application of such a VLSI circuit something very interesting. So I said something like a lookup table. What is it? What is it? It means that if you look at a picture on the right, there is a truth table that I have put similar to what I showed the device. And I have some inputs. Then I say, okay, let us say I want A into B is, let us say C. Okay, then I put all those conditions and I put that code into the computer, that chip, and it will work as so-called AND gate. Now, tomorrow I don't like AND gate, but OR gate. So that is A plus B equal to C. New code, and I take this code and put back into the computer. Now, lookup table means it's like a pigeonhole inside a chip. Now, depending on A and B, what brings me, it will address to different pigeonholes, and the output comes out instantly. No computation involved. So obviously, it is extremely, extremely fast. So fast that, for example, olden days when you had these so-called microprocessors, microcontrollers, and so on, the clock, the crystal, the frequencies decide what is the best frequency that the computer can operate. Now, since this whole thing is in your hand, I can decide what is the clock that can go to that, and I can bring an entire microcontroller code and put it in this, and it operates maybe 10 times, maybe 100 times faster. So this is very important as far as the product designs are concerned. While all these were happening, suddenly one day people found that old transistor which stopped development in 1960s or 70s suddenly found a new life because a bunch of guys in University of California at Berkeley decided to change the structure all of a sudden after 20 years. What they wanted to do, we said that before that there is a base, there is an emitter, there is a collector, and I actually control the base, base drive, which decides what is the total current that I'm flowing. Now that the current density flowing through the base is deciding in some way the function of this whole circuit. Instead of making the base as a single line, can I actually make it like a fin? Fin is like for fish, the fins that you see. Make essentially the cross section of the base much broader. Either use like a omega shape, which is covered on 3, or maybe round around. So then the devices were found to be operating sub nanoseconds, and the densities have grown, and suddenly it opened up brand new handle on the devices, which kind of stopped for 20, 30 years before that. So now you had the same programmable chip, which are million times, let us say, has more gates, million times faster, and so on and so forth. You see how the pace of this development happens. While some people are working, trying to kind of make a nice, architecture of a device in which I can put everything that I can see in a computer all in one chip. It's literally called system on chip. Okay, in a computer, typically you'll have central processing unit, you have memory, you have interface, you have blah, blah, many things. Now, can I bring that entire motherboard onto one chip? What stops you doing it? It's the density of the chip. How many transistors can we put in? Now, if you have trillions of transistors, it makes you to kind of do varieties of things on one single chip. So thanks to the FinFET inventions that happened, it is able to again shrink the size of the chip much, much further, right? So therefore, these all have become kind of reality. You must be wondering, how can somebody do this at a drop of a hat, suddenly bringing the higher densities or shrinking the size? In some way, to make a layman understand this, it is as simple as what you see on the screen, right? We all do this basic geometry, right? Sometime back, we studied what is the resistance of a device is in some way, dependent on the rho, which is the conductive, the bulk conductivity, resistivity, and then the cross section and the length and geometry of the device, right? So I can ask you, if you say give me R, you will say rho L by A and so on and so forth, right? Ohm's law. That now, if I want to kind of scale this device, scale down this device, now if you look at like a square, all that requires is that I need to kind of like taking a mouse and kind of bringing that entire device plane, aspect ratio same. So therefore, it will make me the so-called width into height numbers to be proportional. The same. So that means, given that the material is same, the shrinking of the size is only dependent on what are the actual dimensions. Now, if I'm able to inscribe on the chip using lasers and lithography, etc., very, very fine structures, that means for the same material, I can give you a factor of 10, factor of 100 smaller sizes. So that means there is no magic involved here. It is only the tool that will allow me to kind of make smaller structure, given the same material. Now, tomorrow, if I can invent a newer material whose bulk resistivity is something different, oh, that is even another invention, and that can speed up the entire production or the chip design to a different level. Okay, and this is all this game that was going on when our Gordon Moore, who was that time, I think he was in Fairchild, he kind of, that time there only existed about 50, 60 transistors. We are talking about 1965, you remember? 1950s is the time when you had one transistor. He could actually predict how this whole game of, with respect to time, technology, how the number of transistors per unit chip, etc., is going to kind of grow and so on. It's remarkable. In some way, the vision that he kind of had, even today, to a large extent, we still follow so-called Moore's law, right? Now, I mean, I know it is very dense, and I'm sure you can't see, but what I want to really show in those plots is that on the time axis, the year, and the kind of number of transistors that are produced per year, or the cost of the transistors, or for example, the size of each transistor. On the rightmost, you actually see number of transistors per processor. Right on the top, you actually see, I was talking to Arnav this morning, Apple's companies, the M1 processor, for example, the very first processor that they built by Apple themselves without using Intel. And you can kind of see, yeah, please. Correct, that's right. But here I'm talking about Mac Air, okay, MacBook Air, okay. Yeah, of course, there are different series. See, for different applications, you produce different chips. For example, if you, sometimes they're called RISC processors, RISC, which means reduced instruction set computing. So for different jobs, different areas, you don't need all the functionality that is required, right? When people say microprocessors, they're more of a general purpose devices. But suppose I make a device which is used for image processing, I don't have to worry about all that other functionalities. I only focus on the image processing. Similarly, suppose I want to make a device from where I want to read the data, not so much of image processing. Then my power, that I want to put in is more for so-called input output. Or if I want to communicate fast, maybe few gigahertz, a few gigabytes per second communication, not so much about computing. So I need to kind of see for which area of work that I need to devise. So it's possible that iPhones have faster devices before MacBooks and so on. But the point I was trying to kind of say is that I wish I can read for you what is actually written at the bottom. It's not just the numbers and shrinking of size, but people have really become something so exotic designs of transistors, the dissolvable transistors, the transistor that you can actually swallow and then it gets dissolved because you want to kind of, let us say, the drug delivery devices, for example, and so on and so forth. Devices which are, which are not flat, which are, all sort of exotic kind of ideas come how I can design this transistor. If you have time, maybe later on we'll have a look at the bottom. But so when you look at the timeline from 1948, what you actually see here, maybe you can't read, but the red bands you can actually see. The width of the red band is starting from invention, how long it took to actually commercialize this thing. Okay, it typically takes 5 to 7 years, 5 to 8 years, because there is a lot of processing that needs to go in. It's not just the device, the invention that can change the kind of world. So therefore, somebody like Gordon Moore and others, and IEEE in fact has done a lot of work in kind of trying to predict how, with respect to time or age, year, how this production, the size of the node is going to kind of come down. How much time I have? 5 minutes? 10 minutes. Okay. So you can really see this is a very interesting plot, and it is not so far somebody predicted with dotted line, and so far what is happening, it has not deviated from this line of prediction. That means somebody is really able to did this well. And there is an agency called International Technology Roadmap for Semiconductors, okay, which is actually kind of owned by IEEE, and you can see sitting at around 2020s and odd, we are looking at devices which are 10 nanometers and below. Okay, that is the size of transistor, which is actually helping you to make very, very large scale integrated devices. Okay, and now you could actually look at and see what would happen reaching atomic level kind of dimensions in by 2040s and so on and so forth. But we'll just hold on. We will see the flip side. Okay, so I think I'll skip these few slides quickly. It is only telling how people found what is the way, what is the nomenclature, how you say that what is the node size and so on. There are various standards. But what is most important is people want to kind of understand what is the metal connection from A to B and what is the gate length, gate size in a transistor. Obviously, if they keep shrinking, okay, that brings the entire device smaller. These are just kind of metrics to decide how you say this is 10 nanometer device and 10 node device and so on. I think this one could kind of skip, and let me come to so you can look at this plot. What it is, this slide, what it is telling on the right on top, or maybe bottom, as you kind of see, September 17, 2020, you will actually see a superfin chip talking about 10 nanometer device is unveiled, etc., etc. Okay, just a year later, in fact, much less, maybe 6 months later, you get from IBM a chip which is 2 nanometers. Of course, these are all lab chips. They're not in the market. Okay. May 6th, May 22nd is actually just hardly a week or 10 days later. You will get TSMC coming up 1 nanometer 2D chip. These are all 2D chips. It's a 2-dimensional chip. There is also 3-dimensional. We'll talk about later. Now, what I wanted to really say is that what kind of level of R&D, what kind of level of competition that happens at this moment. We talked some time back in that ITRC thing. We said that is around 10 nanometers is where we are living, but people are talking about in a lab scale. Okay, 1 nanometer kind of level of devices. Obviously, unless somebody had really done R&D and got a reliable results, they don't actually publish this. So this is the kind of competition that happens. Okay, fine. I mean, as I told you, if I have a square, if I want to make a smaller device, I said to take a mouse and take one corner and push or pull. If it is that simple, then are there no problems in technology scaling? Of course, there are lots of problems. So the main thing, as I said, optical lithography, manufacturing of on-chip structures, etc. But the main problem is the area, the power that it consumes, the speed characteristics. Okay, the way the transistors operate, etc., on a kind of planar structures such as MOS devices. That is what we want to improve with, rather decrease, and which will help you with the kind of scaling. But the main trouble right now, what you will have is that when things become smaller and smaller, you will actually want to you want to say that, okay, I want to, those three factors that I kind of mentioned. But if you reach 1 nanometer levels or maybe so, but then you end up, I mean, so then Moore's law almost reaches saturation, and then he doesn't have any ideas on how to do it. So one idea is, again, this is very busy slide, so don't look at it. But the idea is that, okay, let us go up. Means instead of just having one layer, let us actually build layers after layer. Obviously, if I can build another layer, I actually simply double up the uh, the total number of gates, total number of transistors in a chip. Okay, so people started using that. Okay, so therefore people said that, okay, now I'll build so-called 3D. So there is a number of tires, and as well as what we already had as a two-dimensional chip. And for that, it required a slightly different kind of materials. For example, if I want to build using semiconductors, standard semiconductor material, okay, and when I want to use laser techniques to kind of etch structures, when I'm doing at the top one, it is possible the bottom one actually get affected. So it is actually now required that people want to use new structures like linear structures like carbon nanotubes and so on. So the computing elements, the transistor elements, transistor material has moved from silicon and germanium. People are talking about using CNTs if you want to build layer after layer, for example. So now, so this is how the things are driven. There is a science, there are tools, there are engineering, there is a foundry technique. All these kind of take one by one. Now, if I build multiple layers, okay, that's good. But then how do I make interconnections? See, remember we were talking about, I mean, if it is if it is a 2D, then the interconnections are only across them. Now, if it is 3D, then I have to make connections like in a printed circuit board, we call vias. So there has to be conducting things go from, let us say, top from the bottom layer to the next layer. But that will also occupy certain space, certain volume, right? And that if that interconnections are occupying sizable amount of volume, then the total volume also comes down. So people are then talking about, you use kind of tungsten via by which I can bring down the total densities to 25-30%. Then people find, no, that is already kind of occupy, for example, see, this is the estimate. For a chip, the wires occupy 100 kilometers of distance. Can you believe this? It's unbelievable. The whole chip is few centimeters by few centimeters. The complex chip, if you maybe 1.5 inch by 1.5 inch. Now, one is talking about all the wire length that you're talking about hundreds of kilometers. So every small one, not micron, few nanometers of distance, if you can optimize, then you will be able to add the densities to be much larger. So people find what is called a gap fill technology, which is superior compared to, let us say, the wire technology that one had. But essentially, you need to connect up layer by layer from bottom to the top. So that is what improves. So it is from 2D device, it has kind of become 3D device right now. Okay. So the other factor that when you put in billions and trillions of transistors together on a very tiny chip, the problem that you will start facing is the power dissipation, because they consume a lot of power, of course, right? But I also have to dissipate them. If I don't dissipate, the transistor characteristics will affect tremendously. I'm sure as a transistor, we know that if the base current, the current that I'm driving, if it varies considerably as a function of, in fact, it's an exponential function of temperature. So that means the whole device will not work the way I want to work it as a, let us say, switch or an amplifier or whatever. That means I have to maintain the chip temperature reasonably under control. How do I do it? Okay. Then soon, I mean, people found it is very hard to kind of do external cooling. Normally, what we do if something is hot, we'll put a blower or fan or something. But that is only a solution that cannot help the chip inside, right? So what people are finding, remember, there is, yeah. Huh. Oh yeah, okay. So what he's saying is that, for example, if I have a chip, okay, which is actually ceramic, the package is usually with a ceramic, which is not a great conductor of the heat in some way. Ideally, would have liked maybe to have a metal or something. Okay, what he's saying is that you use what is called a heat sink, right? The heat sink is takes off heat from a body, and if I have larger the surface, the larger the heat transfer that happens. But always it happens if I put a metallic thing right on top, the contact is not perfect. No, there is always, no matter how fine the surface is, there is a small air gap which will actually reduce the efficiency of heat transfer. So if you use a paste which is actually basically connecting the load means in this case chip, and the metal contact, the transfer will be more efficient. That is his point. But all of these reach a kind of limit. So now people find that, okay, forget about this lid. So they actually remove the lid. They give you a chip through which you actually can see the transistors if you can. So it's so-called lidless packing has become order of the day. And so therefore, if you want to do like what he's saying, use a thermal shield, etc. Okay, you build it on top of it. But you have ICs these days which do not come with lid. Okay, so that is one idea. The other idea is no, instead of using thermal like what you told about the heat sink, we also use, for example, cooling by liquids. I mean, okay, again, each liquid it has a different heat constant, so you also choose what liquid you want to use, not ordinary water. Sometimes some different fancy liquids. But externally, so you actually the transistor, let us say, the collector into which huge amount of current is coming in, right? All the current is actually collected on the collector. That's why the transistors, the body is usually collector, because so that it dissipates this energy. And then what we do is we run pipes touching physically to the collector, so it takes off the heat, and then you recycle things. Okay, now what? Even that has a limit because the sizes are shrinking. What the companies are doing is the chip itself has a micro needles going through the chip through which you can actually flow the liquid that you want. It is not at the chip level, but it is inside the chip. So you actually have those. If you look at this microfluidic cooling systems, there are channels that are go through the chip, and you can actually keep the chip at cooler temperatures. You can really see how to mitigate all these problems of large scale integration that kind of happens. So with all these games that are going on, this is my last slide, I hope. So what do you look at? There are, as I said, there are many developments, pure science, basic science, like actual chip, how it is produced, the cooling, the various other factors operating at large systems. So if you were to guess 25 years from now, what kind of things that can still work out? Okay, so let us look at it. Okay, so what do you think the transistors will look like in 2047, which is 100 years from the invention? I think I mentioned to you to one of your question that the chips are application specific. You design a chip based on what area of application. So that is going to become more and more, rather than somebody deciding and say, this is my microprocessor and you use it, don't use it, go to hell. Not like that. It is actually the kind of thing. It is user specific. It is user driven, application driven in some way. So that is one. And the second thing is this idea of the MOS device, of FET devices, making on and off based on the field. Generally, that is going to remain at least next 25 years. It's not that a brand new operation that makes 0 and 1 is not going to be seen in the vicinity, for example. And we already talked about the so-called 3D devices, maybe 4D, maybe 5D, I don't know. But the vertical growth of chip is going to be the order of the day, because you already reached the saturation for the 2D device. Of course, low power, low voltage, you remember? Olden days, I started my career working at 12 volts, 0, or minus 12 volts to plus 12 volts. That is the swing. So minus 12 volts is maybe 0, plus 12 volts is maybe 1. Now you talk about 1.2 volts or 0 and 1.2 volts, etc. So the swing that it is going to make you 0 and 1 is changed. Obviously, low power, that is all we want to charge our phone once and use for a whole day, or maybe want to charge a laptop once in one day and things like that. So it's very important. These are the things from user perspective. We want these devices to kind of work this way. The other thing is will transistors still be at heart of most of the computing, or all these quantum computing and other paradigms are going to kind of take over in the next 25 years? The general feeling, the general hunch is that majority of the applications will, at least next 25 years, is going to be still based on the so-called conventional transistor. And now other thing is, just like we are talking about 1901, 1928, etc., 1947, and is that the next device already invented and sitting in CFR or IIT Bombay or somewhere? Still, it has to be only deployed, or is it nobody had ever found that what is the new device that is going to take over? General feeling is that no, it has not yet been kind of done. So maybe the materials which not been invented as that could be the main key. Maybe you are waiting for a brand new material to be invented. That probably will change the device that is coming up, and so on and so forth. The next point is, will silicon still be active part of the transistors in 47? As Arnab mentioned, I think going to probably we can also have a little more discussion after that. There are very exotic materials that are coming on the horizon. So including CNT, which I talked to you when I mentioned about the 3D devices. So those materials, which is completely a different field of material science, could be a key to the new transistor that you are going to see. And then last question to ask is, where will the transistors be common where they are not found today? I mean, you have used transistors in varieties of applications, right? Will you find a new application where transistors have not still penetrated? So it is like now people are kind of talking about transistors being part of your body. I was talking to you, transistors that can be swallowed, transistors on your body giving exactly exact amount of insulin into your body. It is maybe part of your clothing, part of the walls, part of the infrastructure, part of the soil, part of maybe breeze. There may be maybe somebody will spray transistors into this room, and which will be hanging around just like a dust particles around, and then keep collecting data, and you have a brand IoT system which will pick up, self-organize themselves into picking up this data, putting onto the cloud, and so on. Unbelievable. I mean, it's only imagination left to you to kind of see. Since I talked about IoT, this last slide, where now the brand new field of technology integration. Remember, you are talking about semiconductor material using which you make chips, and most detectors and sensors are also made of semiconductors. Instead of building detectors separately and connect them to the electronics, why not you co-build them? Why not you build together? It actually improves the signal to noise. It actually brings time to market. Probably it will reduce power consumption. Maybe it will do many wonders. So therefore now, thanks to all these IoT systems, etc., automated decision making. So the integration of technology, doing together the electronics as well as especially the front end electronics and the sensors have become a brand new field, which is actually doing, I would say, very well. So while we talked about all these transistors, trans resistance, and so on and so forth, that is what you will see in the matrix on the left here, bipolar junction transistor, which is actually feeding current through base, and you are actually seeing the current on the collector, right? I out and I in. You also have the counterpart, which is so-called FET, which is actually voltage operated device. So you have voltage in, and you of course see the current out. But the question to ask after so many years of invention, what this guy asked here on the top right, I have put, he said, why there is no device where I feed current and get voltage output? Why there is no device where I feed the voltage in and get voltage output? It looks natural that you are talking about transistor. Can there be a capacitor instead of a resistive element? So can we have, let us say, a transistor instead of transistor? Okay, and like a Hall effect, right? That is what you do in the bottom, what you see, and this is typically what is an electromagnetic operation. So people are talking, how long you want to live with FET and BJT? Can we look at a new computing element? So that is what I wanted to kind of say. Maybe time has come for a new paradigm of a switching element or a computing element, for example. Okay, so maybe there are all these questions for younger members in the audience and maybe on the Web 2 to look at and ponder whether such things are possible. And I promised that I will end my slide with this, which of course you have already got introduced in the very first slide. But in talking about saying, and in fact, it is the title of one of his talks. I don't remember where he gave, but saying science is a collaborative effort. The combined results of several people working together is often much more effective than could be of an individual scientist working at alone. Obviously, we know this, but what I really want to re-emphasize is you could really see one single, very tiny, humble transistor's life, how many people affected and how many lives it is affecting and poised to affect in the future. It was, of course, never a single person's effort. Even among these three, okay, two are physicists and one is an engineer. And actually, the guy who solved the problem ultimately to actually fix the point transistor was an engineer. Okay, so this is how a collaborative efforts work, and ultimately everyone thinks how to make our life much better. To borrow an IEEE tagline, it is advancing technology for the humanity. Ultimately, no matter what you do, how much you become rich in the process, but when it touches the person on the street, you actually feel great that you have contributed something very significant. Prizes, money, Nobels, etc. come in the way, but I think that is how things are. Thank you very much. Yes.
There's only one online question.
Okay.
I think you answered it partly.
Okay.
Are there technologies to replace the transistor?
Yeah. So, it came, missing devices, I think, which that is a 2018 paper. But actually, people built realistic devices, especially the bottom left one. And I think now again, the same journey, right? The journey that happened in 1940s or 1920s, somebody has to kind of, typically, it is a bit difficult to build capacitors versus resistors. Resistors is so-called polysilicon. You can actually deposit very easily on a transistor, on VLSI process. Capacitors, inductors are much more difficult to kind of implement them. Okay, all this will take time, but this is one. Of course, maybe Adna may have some more insights into it, but quantum, etc., is a big paradigm. It's changing life tremendously. But there also, depending on which technology you want to use for the quantum, there are still a lot of challenges. People talk about building a few tens of qubits and so on. But maybe that's why 25 years, I think general consensus is that quantum is not going to kind of overpower or overtake. But maybe beyond 100 years, there could be new this one coming in, new technology can come in. But meanwhile, all these tricks and traps of building 3D devices and so on and so forth, I think are the ones we need to, that we'll be able to feed for the next 25, 30 years.
Okay, on that note, we will stop the live stream. Online audience, thank you for joining us. And we hope you could get your questions answered. Feel free to write to outreach@tifr.res.in if you have other questions. And those who are here, you can grab a cup of chai and come back for more. We'll stop the live stream. Just to remind you, 2 weeks from now, we will celebrate Copernicus' birthday with a talk on astronomy at the next Chai and Wai session. And the next Chai and Wai session at 6 p.m. a month from here will be on the topic of color. On that note, thanks a lot for watching and goodbye.
Thank you.